Hey everybody, welcome to this class 15A, which is the first class of engineering thermodynamics in block 5. And before we get started, I'd like to say that I really hope no one became seriously affected by this terrible COVID-19 virus. And I also hope the assignment on April 1st went well. And in the coming classes, we will take a look at some very interesting mathematics that will turn out to be very useful for thermodynamics and might actually also answer some of the questions you may have had earlier on. And last but not least, the courses will be taught by Wout Saisau and by myself, Jeroen Koelemij. Now let's start with a one-slide recap of the thermodynamics course so far. Um, so thermodynamics in itself describes different forms of energy and how you can convert one form of energy into the other. And this is a principle that underlies basically any machine or device that we work with or rely on. We have seen, for example, how a power plant converts heat into work and eventually into electrical energy. And we've seen a refrigerator as an example where work can be done in order to transport heat from a cold region to a hot region. And we've seen how airplanes are propelled by gas turbine engines. And the nice thing is that we've learned also about thermodynamic cycles to describe uh, the thermodynamic processes that take place in these devices. So we've seen, for example, the Rankine cycle, which is great because it allows us to estimate, for example, how much work you can get given a certain amount of heat that is added to the system. We've also seen that these cycles, they take place along uh, certain curves, which are special curves in a way that they are either isotherms or isobars, or you have a segment where the entropy doesn't change. Um, so very useful tools also because you can use these diagrams and these thermodynamic cycles to make small modifications to the cycle to increase the efficiency, for example. However, one thing that was still missing was the mathematical functions that describe these curves, like here or here. If we wanted to know a value along one of these curves, we actually had to look it up in a table. And why not use these mathematical functions themselves? Wouldn't that be great? Now, before we proceed, I would like to go back to the tables and the diagrams once more, because why were these tables actually so useful? Well, the tables are useful because they make use of the so-called thermodynamic state postulate, which says that the thermodynamic state of a system can be described maybe by 6 different thermodynamic variables, but you actually need only to know the value of 2 of these variables in order to know the entire thermodynamic state. And that's expressed in this table here. You see that if we know, for example, the temperature and the pressure of a system, then we can just look up in the table following the row the enthalpy and the entropy of the system. And this is something we have done all the time in the previous classes. And the same thing or similar thing applies to these tables here, like the Mollier diagram. And you may wonder what is actually the math that gives rise to these specific curves here. There's another reason why you would like to know the mathematical relationships, because there are all these different thermodynamic properties. Some of them are very easily measured. For example, things like temperature, pressure, uh, the length or the volume of a system, its mass. And once you have measured these, you can use very simple relations to derive the density, for example, from the combination of volume and mass. So far, so good. But what if you want to measure something like entropy or enthalpy? These things are definitely not so easy to measure. And for that reason, it's essential to develop useful mathematical tools so that we can convert things that are easily measured into values of quantities that are not so easily measured, but which we need to know nonetheless. And that's the purpose. Finding the mathematical tools is the purpose of this class and classes 16 and 17 as well. Um, for these mathematical tools, we actually need to learn some new math. And I'm talking here about differentials and about integrals. Now, briefly summarizing what we have just seen, the tables and diagrams were very useful for relating different thermodynamic state variables, but they don't provide much insight. We have seen also, or at least we suspect, that these tables and diagrams are described by much simpler mathematical expressions, and we will soon find out about those. And these expressions, they can be used to convert, for example, measurable state variables like temperature or pressure to other thermodynamic state variables, which are more difficult to measure. And what's important to realize here is that the ability to derive the mathematical relations and to wield these mathematical tools, that this really sets apart the academic thermodynamics course from thermodynamics courses given at other educational levels. Now, this online class is supposed to get you on track a bit, learning about the math, how to use it. But you can get much more information from, for example, the book by Eunice Sengel about engineering thermodynamics. So the subjects of the coming classes are covered in part by chapter 12 of his book. And I would like to highlight in particular the so-called Watt reader, which provides mathematical background in engineering thermodynamics. It was written by Genie Stoffels, a professor at the University of Twente, and the Dutch translation of the title is Wiskundige Achtergrond Technische Thermodynamica, which abbreviates nicely to Watt. So that's why she gave it this name, and we would like to stick to that. The reader is posted on Canvas, and the first part describes all the math and the thermodynamic relationships that you would like to learn about. It also contains a whole bunch of exercises which can be found in part 2 of the reader, as well as answers that are given in part 3. So thermodynamics often deals with changes in properties during a thermodynamic process. And in these thermodynamic processes, we often assume that the whole system is in quasi-equilibrium, which means that even if there's, for example, mass flowing into a system, then the same amount of gas per unit time is flowing out of the system through another boundary, so that the system can be assumed to be in sort of quasi-equilibrium throughout all the stages of the thermodynamic process. Now, to calculate changes in a process or in thermodynamic properties, it's helpful from a mathematical point of view to divide the change down into very tiny steps, these infinitesimally small changes, because these can be evaluated using differential mathematics. And for this reason, you will encounter many thermodynamic relations that in fact involve differentials, like, for example, the Clausius equation, or the boundary work done by an expanding gas, or the Gibbs equations that you see here. Now, we know that according to the state postulate, a thermodynamic state has always at least has two independent properties or variables. So mathematically speaking, a thermodynamic state is always written as f, a function f, as a function of the variables x and y. For example, the volume, which can be written as a function of the pressure and the temperature. Now, when you want to derive the differential of such a two-dimensional function, you need to introduce a new type of derivative, the so-called partial derivative. Let's start by taking a look at a familiar concept, and that's the derivative of a, well, let's call it a normal function, which depends only on one variable, for example, a function f of x. Then the derivative, it basically quantifies the steepness of the function f at a certain value. Let's call this value x naught. So it's something that's depicted here in this graph. You have this function, and there's also a mathematical definition of the derivative, which is expressed in terms of a limit of this interval delta x going to 0. And here is an animation that shows actually what happens when you take this limit of delta x going to 0, and you see also this tangent line here. This approaches in the limit that delta x goes to 0, it approaches the derivative or the slope of the function f at the value x naught. More formally, you could also say that the derivative of a function is equal to the rate of change of a function with the variable with respect to which the differentiation takes place. Now, don't look at this formal definition for too long, because in practice this is not really what we use. When we take derivatives of function, we always use simple differentiation rules, like the one, for example, denoted here. Well, like we saw before, thermodynamics deals with state functions that have at least two variables. So let us consider now a function z of x and y, which is defined on a two-dimensional plane x and y. Now we can look at the variation of z with the variable x while keeping the value of y fixed. And this variation in this case is what's called the partial derivative of z with respect to the variable x. And it's shown here in this graph. So the function z is assumed to be a surface of a sphere. And like I said, we can keep the variable y constant, so that defines a plane that intersects with the spherical surface. And along this surface, we can draw a tangent, and like is shown here. And the slope of this tangent is essentially the partial derivative. And if you look again at the formal definition of a partial derivative, you see that it now involves a function of more than one variable, but the definition itself looks very much like the definition of a normal derivative. Yet things are different, of course, in particular in the notation. It has this curly d that is used, and that always indicates a partial differential or partial variation with respect to only one of the variables of the function z. Whereas if we use a straight d, this indicates a total variation. If I would use a d in the context of this function z of x and y, it would indicate a variation with all those variables together. We will see more about that on the next slides. Note also that the value of a partial derivative, this dz dx here, it's always given for a certain value of y, and the value of the derivative generally changes when you take a different value of y. In this curve, that means that if we would take a different value of y, then this intersection here would actually move, and obviously the tangent would have different values. And just a small detail, but probably good to know, that if you have a function with even more variables, for example 3, the function p of x, y, and z, then the partial derivative is denoted as, for example, dp dy for fixed x and z. This partial derivative is always taken with all the other variables held fixed, and you explicitly mention all these other variables. If you have a function with only two variables, like this z here, then of course there's only one other variable, so you will see only one variable here, and this is often the case in thermodynamic mathematical relations. Now let's take a closer look at this total differential. So we have our function z of the variables x and y, and we can write the total differential as follows. Let me pull up my pointer. We can intuitively understand that a variation of x by an amount of dx will lead to a variation of z. And we can also understand that a variation of y by di will lead to a change in z. But what are the proportionality constants? Well, that's exactly what this partial derivative is, because it tells you the rate of change of z with a variation of x. So if we take this rate of variation, this partial derivative dz dx at a fixed value of y, and if we multiply that then with the size of the variation in x, we get the contribution to the total differential. And the same goes for the second term here. We take the partial derivative of z with respect to y at a fixed value of x and multiply that with the variation dy to find its contribution to the total differential dz. I think I've said it before, but just once more, x and y are independent variables. Z obviously is a dependent variable because it depends explicitly on x and y. And this is quite a fundamental relation and generally applicable. And we will see more examples in the upcoming slides. You may also take a minute to look at this geometrical representation of the total differential. So it's the same thing as what's shown here in mathematical form, but now in the form of a sort of a surface element. And by surface element, I mean it's part of a bigger surface that may have curvature on a large scale, but this element is so small that you can approach the surface by sort of linear segments. And well, just take a look, and it might give you some additional feeling or intuition with the concept of a total differential. You should also be aware that in the world of derivatives and partial derivatives, there are different notations around. In math, or mathematics, you will sometimes find a notation like this, f subscript x or f subscript y, which then indicates a derivative or a partial derivative of the function f with respect to the variable x. And you can also have double derivatives, f double x or f double y, and this differs from the notation that we have used so far and the notation that is commonly used in mechanical engineering, because we like to use this partial derivative expression in the form of the curly d's, and also explicitly mentioning which constant is being held constant or is being fixed while computing the partial derivative. That's actually a very helpful aspect of our notation. For example, you can take a look at the heat capacity. There's the Cp that we've learned about in a previous class, and there's Cv, and we know these are completely different things. But if I look at the expressions, they look terribly much the same. There's a T, there's a ds, dt. The only difference really is in which of the two variables, pressure and specific volume, is held constant at the time of the partial differentiation. Now, so much for the mathematical definitions. let's go back to thermodynamics again. And as a simple example, let's take a look at an ideal gas. And we know that an ideal gas involves things like volume, pressure, and temperature. And in fact, we can write the volume as a function of pressure and temperature, like it is done here. And I have to bring up my pointer again. This is the function that I'm talking about. Now, of course, we know that there is actually a more exact form for this expression because we know the form of the ideal gas law, PV equals R times T. But for the sake of argument, let's assume that we don't know this form. So let's stick to this more abstract form for a minute. Now we can write down the total differential of this function v as follows. The total differential dv is again the sum of a partial derivative times dt and another partial derivative times dp. And in this case, p and t are considered the independent variables, and v is made explicitly dependent on p and t. Now in the following movie, Wout will show you how to proceed with the analysis of this total differential dv.
Welcome to another video, about thermodynamic property relations, and especially about partial derivatives. And in this video we will discuss how a bag of crisps, the volume of a bag of crisps behaves. And during this video we're going to take this bag of crisps for a walk up to the Himalaya from point A to point B at the top, point B, and here we have a temperature TB and a pressure PB. Over here we have a temperature TA and a pressure PA, and of course we have here our bag of crisps. So crisps, and well, at high in the mountains pressure is very low, so PB is lower than PA, and high up in the mountains temperature is usually lower than temperature at sea level, TA. And we're going to bring this bag of crisps with us to the top of the mountain. So the bag of crisps actually undergoes a process. And to show you an example of a process and what happens during this process from point A to B while lowering the pressure, we have a short movie. So please enjoy. Over here we have a vacuum chamber which I connect to a vacuum pump, and I'm going to show you that by lowering the pressure in this vacuum chamber we can actually increase make the volume of the bag of crisps increase. So there we go. We know for sure that the volume of a bag of crisps, and we're just going to consider the amount of air that is inside the bag of crisps. We know that it's dependent of the pressure and temperature. And it is dependent of pressure and temperature by the ideal gas law, RT over P. And we're actually very interested in how the volume of the bag of crisps changes. So we're interested in change. So we're interested in dV, the change of the volume. And well, if I want to know something about dV, we've already learned that we need to take the partial derivative since temperature and pressure are involved. So this will lead us to the following differential equation. dV is equal to the partial derivative of volume with respect to temperature for a fixed pressure multiplied by dt plus the partial derivative dV over the pressure multiplied by dP. So here we have our total derivative of the volume. And using this, and of course we are going to assume that dt and dP are very small, so everything is in quasi-equilibrium. So we're going to, well, cut the process in very small slices, but in the end we can get a good view of the behavior of the bag of crisps, of the volume. Well, since we know our function of the volume, RT over P, we can actually calculate dV over dt for a fixed P, which is the derivative of the volume with respect to temperature. And this will be R over P. And it's actually the same as V over T. Use this equation and you will find out. Please check it yourself. And we can determine the other derivative, partial derivative dV over dP with respect to a fixed temperature. And this is, well, actually minus RT over P squared, or equal to minus V over P. So here we have our partial derivative of volume with respect to pressure. Okay, so our total integral will look like this. dV is, let's just say now R over P dt minus R over T P squared dP. So this is the total derivative of the volume. Now, of course, I'm interested in the behavior of this bag of crisps, of the volume of the bag of crisps. So I'm going to draw the diagram, the surface related to the volume. And the system of coordinates looks like this. Over here we have our temperature, T. Over here we have the pressure, P. And over here we have the volume, V. And to make this diagram, I have to check how my volume behaves for instance, a fixed T or a fixed pressure. So I'm going to fix my pressure. Then volume will behave like a constant multiplied by the temperature. So R and P are both constants, so it will be a constant multiplied by the temperature. And in my graph, it will look like this. So a constant multiplied by the temperature, so a straight line. So now I'm going to fix the temperature. So for a fixed temperature along the pressure line, I'm going to study the volume. So that will behave like RT is a constant over P, thus a constant divided by pressure. So that will look like something like this. So 1 over a variable. Well, and I know if that happens here, behavior will be the same this side. So I can just try to draw a parallel line, and over here behavior will be comparable. Okay, so let's assume, so this is the surface of the volume. So this is how the volume is described by pressure, by temperature. You may remember this surface from the exercises, the PVT diagram. Now I'm interested in the behavior at some point along the, at some point in my diagram, at some temperature and some pressure. So I'm just going to, well, at first I'm very interested in what happens for a specific pressure. So, and let's say that's this pressure. So there will be a line here for this pressure. So for this pressure I have my CT diagram, and at some point I'm interested in the behavior. Well, and since I already know that my dV dt for a fixed p is equal to r over p, so equal to a constant since p is fixed, I know that my derivative over here, so my rate of change over here, is a fixed value, so a constant value. So over here I can show you I have my dV over dt, so my rate of change due to temperature for a fixed pressure, which is equal to r over p over there. I can do the same in the other direction. So on this line, and for instance check the behavior over here. Then I can make my derivative will look like this. So it will describe the rate of change, and my derivative in this point will be dV over dP for a fixed temperature, and it will be equal to minus V over P. Well, and this I think it makes some sense, since if we lower the pressure, the volume will increase, like you can see over here. So for a fixed temperature. So, and that's actually what we saw in this experiment. When we decreased pressure, volume increased until it could no longer increase, and the back of crisp would open. So I hope this example gives you a bit of a feeling why we need these partial derivatives and what's the use of them. And I hope this will help you to apply the partial derivatives in completing your assignments and your project. Good luck.
So like we just saw in the movie, the total differential dV can be expressed as shown here in this line. And in this case, we were actually lucky because we knew beforehand the exact functional form of the ideal gas law. We know that it is PV equals RT, so that makes it easy to calculate all the partial derivatives that we would like to know about. Things will get a little more complicated if you're using a different equation of state to describe the ideal gas, or let's say it's an almost ideal gas, because there's, for example, the van der Waals equation of state, which is a modified version of the ideal gas law. And what van der Waals did, he included the effects of two more things. The first thing is he realized that the molecules in a gas are not point-like particles, but they are kind of spheres that have a certain volume, and they are hard spheres. They can collide, but they cannot penetrate into each other. So there's actually some part of the volume that's occupied already by the molecules, so there's less volume for them to move in around. That's why this term B is introduced. And van der Waals had also discovered that molecules, when they get close, they start to attract. You can imagine that that has a small effect on the pressure, which is also modified, and that's why this specific term proportional in this A, this factor A, is added to the equation. And if you look at this equation, well, you may stop for a minute and try to think how you would derive the units of this A factor and this B term. Well, of course, we can calculate partial derivatives also for this state equation. So in that sense, we're lucky. And exercise 3.6 is actually devoted to finding the partial derivatives for this particular equation of state. Okay, but now what if the equation of state is not so simple, like we saw before with the ideal gas law? In fact, in many cases, we don't have a simple mathematical expression, for example, in the case of water vapor or steam, or when you express things in terms of enthalpy or entropy. And we still have this idea in mind that we want to be able to convert things that are easily measured, like P and T, into things like entropy. And let's take a look at this particular total differential ds, where we make the entropy dependent on the pressure and the temperature. Well, this all makes sense. This is what we just learned. This is how you write out a total derivative in terms of partial derivatives with respect to the independent variables. But now the question is, what is in fact the expression for this partial derivative, or what is its value? Or let's consider yet another quantity, the enthalpy, which we can express in terms of temperature and entropy. And again, we can write down this this expression in terms of partial derivatives, but still we don't know what the values or the expressions are for these partial derivatives. Now, in some cases, we can actually find a solution to the problem in the following way. Let's take a look, for example, at the internal energy, U, which can be expressed in terms of the entropy in the specific volume. And then using the rules that we just learned, we can write down the total differential for du. Or take a look at the enthalpy as a function of entropy and pressure. We can also write down the total differential for that. And hey, this is interesting now because in class 5, we learned, actually we derived the Gibbs equations. This is one Gibbs equation which can be derived from the first law of thermodynamics in combination with the second law of thermodynamics. If you want to know how that went, you can go back to class 5 and look it up. It's all written down on one slide. And there it was also shown how you can write down the second Gibbs equation. And if we compare the form of this of these two equations, then we realize, hey, wait, this is exactly the total differential that we would like to write out in full. And it turns out, on closer inspection, that this partial derivative is actually equal to t. And this partial derivative is actually equal to the minus p shown here. So in this case, we can find partial derivatives from equations that we had derived earlier on. It also allows us to define temperature in a different way. Temperature is here defined as the partial derivative of internal energy with respect to entropy for a fixed specific volume. Now, intuitively, also to me, this doesn't make much sense. But just rest assured that if you, for example, if you take a gas which consists of molecules that are moving around, then we know that the temperature of the gas is associated with the velocities of the molecules. Now you can describe a gas like that, and you can write down a function for the internal energy. You can find a function for the entropy. We're not going to do that in this course, but in principle it can be done. And if you then evaluate this partial derivative, then indeed you end up with the temperature, which is the same temperature that you would get if you would look at it from the point of view of particles moving around with a certain velocity. And let's look at yet another thermodynamic function. Let's not look at the internal energy as a function of entropy and specific volume, but let's interchange the roles. Let's assume that internal energy is now the independent variable and entropy is the dependent variable. So we can write entropy as a function of internal energy and volume, for which we write down the total differential as follows. And we can again invoke the Gibbs equations to make our life simpler or find solutions to problems, because we can, for example, rewrite this differential ds in the following form. And we can compare the expression for the total differential ds here with the one written down here, and we see that the partial derivatives are equal to, well, 1 over the temperature. And here you will notice that this is actually the same definition of the temperature that we saw before, but inverted. 1 over T, and here du and ds have changed with respect to, they have swapped positions with respect to the expression that we saw on the previous slide. And we have an expression here also for the partial derivative ds dv. We have seen those before in class 5, where we learned about entropy, about the general behavior of entropy, and combining that with empirical observations of how thermodynamic systems behave, we figured out that that if the internal energy is increasing, then entropy must be increasing too. And if volume is increasing, then entropy should be increasing too. And lo and behold, if we look at the total differential, which indeed describes the variations of entropy with a change in internal energy, we see that if this one becomes bigger, or if there is a change du that's positive, then multiplying this with the partial derivative, which is 1 over t, which is also a positive quantity, automatically leads to an increase in the entropy. And the same goes for an increasing volume. If dv is positive, we multiply it with a quantity that's also positive. So we see an increase in entropy. So the things that we kind of semi-empirically derived in class 5, we have now proved mathematically. And everything turns out to be as expected. Great. Now here you see a slide that you've seen before. It's stuffed with equations, useful equations and relationships that you've learned about. It doesn't hurt to try and memorize these occasionally, and also perhaps the form of the phase diagram here with the vapor dome. Before I get to the final slide, Wout and I really would like to thank Genie Stoffels of the University of Twente for letting us use and edit her fantastic engineering thermodynamics slides. Okay, we've reached the final slide, and now it's time to activate your long-term memory. So after I stop talking, just take a minute, and it really doesn't have to take more than 1 minute. Just take a minute to reflect back on the lecture and try to decide for yourself what was actually the purpose of this class. And can you think of 3 elements which were eye-openers for you, or which you consider to be key elements of this class? And last but not least, always feel free to approach us to, well, ask any questions or send comments or suggestions to us. All right. See you soon in the online class. Bye.